Hey, how's it going? We're going to talk about boiling point elevation and vapor pressure in this video. All right, so whenever you add an ionic or polar compound to water, you will also raise the boiling point, make the temperature at which water will remain a liquid higher than at 100 degrees Celsius, which is its normal boiling point. So let's give an example of this situation. So the reason your car has a radiator, as mentioned in the previous video, is to move heat away from the engine block to cool the engine down and prevent the metal in the engine block from melting. And it does a pretty good job of that. But if it was a really hot day, say it's 100 degrees out and you're working your engine really hard, it may be that you're not able to move enough heat out of the engine, and the water in the radiator would get above 100 degrees Celsius and would want to flash to steam, would want to turn into a gas. Now, what would happen in that situation is if the water were to go from liquid to gas, it would expand rapidly and cause your radiator to explode in a steam explosion. Now that would be really bad because that would mean you'd have a destroyed radiator and your engine block would probably start to heat up and melt. So in order to avoid that catastrophe, radiators also have a pressure cap, and that pressure cap is designed to burst open and release that excess steam pressure before the metal of the radiator actually ruptures. And so if you've ever had a situation or seen a situation in which a car is steaming on the side of the road, that's a situation in which the pressure cap has popped, releasing that steam into the environment but preventing the radiator itself from exploding. At that point, you need to pull over because your radiator is not able to move heat out of the engine block any longer, and you don't want to have any extra damage. Now, there is something we can do to kind of mitigate this problem and make it far less likely. We can add a substance to water that raises its boiling point, and that's what antifreeze also does. Antifreeze not only lowers the freezing point, but it actually raises the boiling point. What that does is it allows the water to remain a liquid at a higher temperature. The longer it remains a liquid at a higher temperature, the less likely gas will form and the pressure cap will burst, and the more it can keep trying to move heat out of the engine block and prevent overheating of your car. So antifreeze is great for both preventing freezing of the water and raising its boiling point. So this boiling point elevation is related to a concept called vapor pressure. Vapor pressure refers to the amount of gaseous substance that sits above a liquid in a sealed container. So at all times, liquids are basically having some of their molecules evaporate out of the solution because they've gained enough kinetic energy. Now in an open situation like a cup of water just sitting outside, that water vapor can just go into the atmosphere and disperse away with the wind. However, if you have it in a sealed container where it's not able to escape, then some of those water molecules, as they're in the gas phase, will go back into the liquid phase, and you'll have an equilibrium where some are evaporating out, some are going back, and the amount of vapor in the container remains the same at all times. You've probably seen this process occur if you've got a water bottle out that's sealed, and you notice little droplets of water forming on the sides of the container. Those water droplets are the water vapor recondensing into a liquid. When you add a solute to solution, a salt or a sugar, the water molecules will attach to those solutes and form these hydration spheres. Because those water molecules are locked in, attached to those ions, they are not free to escape as a gas. And so the more solute you add, the more water gets occupied by those ion-dipole interactions, and the less they're able to escape into that vapor phase. So we lower that vapor pressure. In order to make water molecules evaporate, to get to the boiling point where they can turn into a gas, we're going to have to add even more heat to the system so that those water molecules are moving faster and faster and faster and can overcome those ion-dipole interactions to escape into the vapor phase. So that's why the boiling point will be raised when you add substances into the water. because we have to heat them up higher to overcome the intermolecular forces that are holding them in the liquid. So this is just a diagram showing the what we would say is the vapor pressure, the number of vapor molecules. So in this first phase right here, it's just the pure substance, and you can see the quantity of vapor up in this area relative to the liquid. When we add that solute in there, and that interacts with the water, it reduces how many of these molecules are able to stay in that vapor phase. Pressure has an impact as well on the boiling point of water, because the higher the pressure of a gas sitting on top of a liquid, the less those molecules are able to escape into the gas phase, because every time they try to escape, they get knocked into by molecules in the vapor phase, like air, and the air molecules can essentially force them back into the liquid. So the higher the pressure, the harder it is for those molecules to escape. So, if you go to higher and higher elevations, the air pressure lowers with higher elevations, and the easier those air molecules can escape into the gas phase. That lowers the boiling point because it takes less energy to get them to turn into a gas. So you can see this chart here. So this is in elevation in meters, and what you can see is at sea level, the temperature of boiling is 100. But as you go higher and higher in elevation, the temperature it takes to boil it drops down. So in the city of Flagstaff, Arizona, that city sits at 7,000 feet. There, water boils at 94 degrees Celsius instead of at 100. Up on top of Mount Everest, water boils at about 75 degrees Celsius. So the higher up you go, the easier it is for water to boil, the less energy it needs, the lower the temperature it needs to be for it to boil, because there's less holding it in place. In fact, if you were to have a pure vacuum and you dropped water, liquid water into a pure vacuum, it would evaporate almost instantly because there's nothing holding it in place except its own intermolecular forces. And once they escape, they're gone. Now, one way that you can raise the temperature at which the water will remain a liquid is that you can put pressure on it using a pressure cooker. So if you were to put high pressure onto the gas, you're essentially forcing those molecules to remain in the liquid phase. So one of the ideas of a pressure cooker is that you can cook your food a lot faster. It seals in the gases, increases the pressure inside, and that means that the water remains a liquid at higher and higher temperatures without turning to a gas, and that cooks your food faster. Pressure cookers are particularly useful for people who live at high elevation, because if you live at high elevation, it takes a lot longer to cook your food, because the temperature of the water doesn't get as high before the water boils. So just living in Arizona myself at Flagstaff, I would have to cook my pasta for, say, 10-15 minutes longer than I do at sea level here, because the boiling temperature of water was lower, and so that it wasn't as hot, and the pasta took longer to cook. Using a pressure cooker speeds up the cooking time by increasing the temperature at which the water remains a liquid. Now, another example of using pressure to maintain a liquid at higher temperatures is a propane tank. So propane wants to be a gas at room temperature. Its boiling point is 1 degree Celsius, which is barely above freezing. So if you were to open up a propane tank, it comes shooting out as a gas. But by forcing that gas to about 5 atmospheres, or 5 times the pressure of sea level, you basically force those propane molecules tighter and tighter and tighter so they have to stay a liquid. And what that does is it allows you to put a lot more propane into a tank than if you just had a tank full of gas. Because gases are denser than liquids, if you were to force more propane in as a liquid, you could get a lot more propane in the tank, and it's a lot more efficient to transport it around and keep it on site and so forth. Okay, those were colligative properties.